primarily with Professor Michael Thompson, and I also work closely with Professor Bruce Vandover, Professor Colin Gomes from the CS department, and Dr. John Gregoire in Caltech. And today it's my pleasure for me to share some very new work we've just done in like a couple of weeks ago as the integrated, autonomous, and user-guided active learning for targeted material synthesis. So I know many people here are theorists, so I want to be clear about our experimental setup. So we have this very special technique in our lab, which is a lateral gradient laser spike annealing. So laser spike annealing is a technique that was applied in semiconductor industry, mostly for dopant activation, but we modified a little bit so that it's more useful for scientific research. So basically, we focus laser into a bi-Gaussian beam so that there is some temperature dependency on the x-axis. As you can see, this is our beam, which is about 1 millimeters wide and 200 microns in the scan directions. And we shine this high power beam onto our sample, which we deposit metal oxide thin films on top of silicon wafers. And as the stage moves away, the heat gradually, it will heat up the silicon wafer, and the heat will be conducted to the thin films, and hopefully it will transform the amorphous film into something crystalline. And so with these methods, we can reach a really high heating and cooling rate at about 10 to the 4th to 10 to the 6th Kelvin per second, so that we can look at something that is very far from equilibrium or metastable regime. So this is a really high throughput method. We can do like a stripe within 5 seconds. And the temperature distribution really allows us to probe the phase behavior within one stripe at various different conditions. So after the film is being annealed, we can do a number of characterizations to see what phase has actually formed. So then we can map it into a processing phase diagram. We call it a processing phase diagram, which the x-axis is the dwell time, which is basically how long the material has experienced the peak temperature, which is the y-axis. So we work with temperature range of about 400 to 1400 C, mostly limited by the melt of the silicon. And the dwell range is about 250 microseconds to 10 milliseconds. And in addition to these two conditions, we can also have deposit thin films that has composition spread, so that at each location on the wafer, we have different composition, so that we can deposit a number of different elements on top of the films. So this phase space really grows exponentially as you add more elements into it. So this is also now a resource management thing, because once this our anneal is destructive, so once you anneal it, you cannot do another experiment on that condition again. So then this is a good place that we can introduce some active learning things, schemes into this. So we recently developed this scientific autonomous reasoning agent, or we call it SARA. So basically in material science, we often fall into this processing, characterization, and evaluation research paradigm. And now what we want to do is to have an AI, an automated robot, to take over everything so that we can just look at the results, basically. So this is the implementation of that. So we still start with the laser spike annealing, and after each of the steps, we will do a optical characterization. And mainly, we're looking at the reflectance spectroscopy to see where at what condition there is a strong change in that. So that would indicate a phase transition. And however, that measurement is quite costly. So we use a low-cost optical image to do a strike-specific kernel design to accelerate this active learning process. So once the gradient along the x-axis is learned, it will pass into a global active learning agent, which we have a Gaussian regression to basically have a surrogate model of the global phase space, and then using some, again, a specially designed acquisition function to decide the next synthesis conditions. So we greatly reduce the redundancy in the experiment and speed up the whole process by 70 times when we compare to our research. So this was published two years ago. So if there's a lot of interesting math that goes into this. If you're interested, you can check out the paper. But now we're moving on. So we're thinking, so that mode was purely explorational. So it's not really exploiting a lot of physical insight of the system. So how do we expand that to answer more specific scientific questions? For example, is the phase pure? Or if we want to find the phase region for a specific phase, or is there any phase coexistence? And if there is that coexistence, what is the phase fractions and their uncertainties? So this requires on-the-fly phase labeling and crystal structure determination within the time scale of our experimental loop. So now we need a high throughput XRD and also on-the-fly XRD analysis. Okay, so I mean, high throughput XRD is readily available. If for thin films to go to a synchrotron facility, you can get high throughput XRD easily. So what we develop is the on-the-fly XRD phase labeling methods. So we call it the crystal shift, which is physically realistic and probabilistic multi-phase labeling algorithm. So this is a high-level overview of what's going on in this algorithm. We start with a list of zip files. We construct a tree trying to enumerate all possible phase combinations. So to make it more concrete, so we have alpha phase, beta phase, alpha plus gamma, alpha plus, and so on and so forth. And so we have a best first search algorithm, and which will select the most probable phase combination to and pass it to the crystallography realistic optimization algorithm, which uses a regularized LM algorithm while preserving the symmetry of the phase. So we're changing the lattice parameters without breaking the symmetry and try to match that pattern. And afterwards, we'll pass the result back to the best of search algorithm to further select the phase combination to be optimized. So this is a back and forth process. And once we think the tree is explored sufficiently, we'll use those results to estimate the probability of the presented phases, and based on the Bayesian model comparison and Laplace approximation. And the outcome will be the probability versus the phase combination distribution. Then we can sort it and return the top candidates. So each of these candidates will contain the following information: their phase combinations and their activations, the corresponding probabilities, and their refined lattice parameters. So this is a high level, just going through this at a really high level. This should be published soon, so keeping. And the nice thing of this is that since it's a probability, it returns the probability, but you don't know how good the probability is. So what people usually do is they do a calibration so that the predicted probability matches the frequency of correct matches. For example, if you predict that a phase should exist 50%, then half of the time that should be in the ground truth. So ideally, you should have a diagonal line. So the advantage of this method is that it's easily calibratable, and unlike other neural network methods, which is likely be affected by noise because this is a Bayesian methods, Bayesian follow Bayesian methods is less likely to be affected by noise level. And this, you have to take my words for it, is that we have tested it and it performs better than other counterparts that provide probabilistic and multi-phase labeling methods. And the additional benefits of this crystal shift method is that we can have quantitative lattice shift and peak broadening, and it's mutable on the fly because we can just remove and add phases without needed to retrain the neural network. And we can also jointly optimize a smooth background. And we can deal with some amount of texturing, just the peak ratio. If the peak ratio isn't ideal, we can still deal with that. So with that, equipped with that, we can improve our Sarah workflow. So we still start with the laser spike annealing. And then now we do a high throughput XRD. So we go to a synchrotron facility. The great thing that is that there's one on campus in Cornell. So we can scan and microbeam XRD X-ray beam across the stripe and produce this beautiful X-ray heat map. So we start with amorphous, get something crystalline, some phase transition, and then back to amorphous. And then, because that's too much data, we have to do some dimensionality reduction. We have non-negative matrix factorization to factor out the main bases and their corresponding activation along the x-axis. And we'll pass the bases into the crystal shift, and it will return the top candidates. So to combine them again, we have to do a combinatorial thing and then merge with the activation to get an expected phase fraction, phase activation for each phase, which should look like this. So most of the phase is inactive, and some of the phase you have a finite activation. So at this place, we also did a GP just to smooth out and get some uncertainty measurements. And then we'll pass through a global GP to model where the phase present in the global condition space. And for each of this loop, we're trying to optimize the activation of one of the phase. So we use an expected improvement acquisition function to select the next experiment. And the nice thing of this is that along this, we'll have some human expert that can intervene with the process. I'll talk about it in more detail later, but just put that in mind. Okay, so we tried this thing about 3 weeks ago. So it's a targeted phase synthesis in bismuth titanate system, and it is also a composition spread thin films. So we start with the titanium rich and go all the way to the bismuth rich. So basically pure bismuth oxide to titanium oxide. So there are some phases that we're particularly interested in and want to see where it will show up. So the annotate, rutile, 2411 phases, and the parachlor are photocatalyst, and the aryl phase, or 4312 phase here, is the piezoelectric ceramics, and delta is like high-performing oxygen ion conductor. And so what we did is we start with 12 candidate phases. So at each of the iterations, we're trying to optimize one of the phase, and this is a global GP of the annotate phase. And we started and then went to a coffee break, just like what we did. And we came back and look at the global GPs and think that, okay, I think some of the phases not going to show up and we're not interested enough. So we moved those phases and left with 8 candidate phases. And then we let it run for a while again. Then we found that only 3 of the phases that were interested, and the phase regions are still not well defined. So we let it run for a while with just 3 phases. So the human here is acts the role of like looking at the result and further optimize like what are the most important objectives for this experiment. So it starts with a exploration stage and then gradually turn into a targeted or more exploitation stage of this. So as you see that imaging 3D space is really hard. So what they did here is take the slices at different composition and then turn it into a animation. So this is again the annotate phase. It gradually disappeared as you add more bismuth content. So these are the phase field for the 6 phases we're interested in. So you can already see some phase coexistence for this. And as I start the animations, you can see all the phases. The titanium-rich phases gradually disappeared, and the parachlor show up, and in the end, there's our bismuth-rich phases. And to note that these are all performed autonomously, and to produce this, we only have to do 120 samples, and we haven't really done a math or test, but I think we'll have to do at least 5 times more if we're doing a random search or just grid search. Okay. So to conclude, we have developed a XRD labeling algorithm that operates at a timescale commensurate with our experimental loop. We combine that with the Sarah framework to demonstrate an autonomous targeted phase synthesis workflow with active learning, and it allows optional user intervention. So you can just have coffee throughout the experiment, but you can also change something on the fly. And on this system, we have found high conversion conditions for phases that we're interested in. So this is our group. Particularly want to thank Sebastian, Max, and Duncan Unfortunately, or fortunately, they're all doctor now, so they left only me. I'm still carrying on this project. I also thank our collaborator at Caltech and our beeline scientists and CHESS and all of our funding agencies. Thank you for listening, and I welcome any questions.
Patrick?
Thanks, very impressive work. I had a question on the SARA part that you presented at the very beginning. You had a comment there that you used a specialized kernel for the GP.
Yes.
I was wondering if you could say more about it, because the space you're scanning is highly discontinuous, right? When you have phase boundaries between the different materials.
Yes.
So nothing smooth would work for that.
No, so basically, because in the optical images, you can also find transitions, but that transition may not necessarily be a phase transition, right? So what we did is we sort of sneak that information by looking at the gradient in the optical image and make some modification to the kernel design. Sort of cheating, but it's useful.
More questions? Okay, so let's thank the speaker again. Next, we'll have a contributed talk by